In this video, we solve problem 14.2.057 from the Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. Problem statement says, the Cobb-Douglas production function for an automobile manufacturer is f of x and y equals 100 times x raised to the 0.6 power times y raised to the 0.4 power, where x is the number of units of labor and y is the number of units of capital. Estimate the average production level if the number of units of labor x varies between 450 and 500, and the number of units of capital y varies between 575 and 600. Now, they asked us to estimate the average production level, and that is related to functions of several variables in the following way. If I have a function of several variables, and I want the average value of that function over a certain region. So maybe my function of several variables looks like this if I were to graph it, and I want the average value of that function over the region R. Basically, what you're going to do is you're going to take the volume between that function f of x and y and the region R in the xy plane. And then you'll divide by the area of the region R. And that will be defined to be the average value of f over the region R. So basically we're saying, what's the average z value? What is the z value that I would multiply by that area? So that z value times the area gives me the volume under the surface. So it's as if we took this surface, which is varying, and we replaced it with a horizontal plane. We want to know what the equation of that horizontal plane would be. What is the z value for that horizontal plane, so that the area between that plane and that region R is the same as the volume under the surface. That's how we find f average over a certain region, and the volume between that function and the xy plane is given by this. If that function is non-negative, if the function is sometimes negative and sometimes positive, this would be a net volume. We take volume above the surface and volume below the surface, and we would subtract. And we would want those positive and negative values as we compute some average. So this is going to stay exactly the same. We're really taking a net volume here. But then we'll take that and we'll divide by the area of the region R, which can be represented this way with a double integral, or if it's a really simple region where we already know a formula for the area, we can use that as well. So that's how we find the average value of a function of two variables. Now this is in a particular application problem, but even if we don't know anything about this Cobb-Douglas production function, or what they mean by a number of units of labor and a number of units of capital, I don't know what exactly that unit of labor would be, or what they mean by a particular unit of capital. It's not clear from the problem statement. We still have enough information to find the average production level for this function. We're just going to use this formula. And the region R is described by these bounds. We're told that the number of units of labor X varies between 450 and 500. So we know that's true. And we know that the number of units of capital Y varies between 575 and 600. So X and Y are both going from a constant value to a constant value. So if I were to look at this region in the XY plane, X starts at 450 and ends at 500, and Y starts at 575 and ends at 600. My region R is just a rectangle. Easy breezy. And we can find the area of that rectangle pretty easily. It's just length times width. So that's the area that will go in the denominator, and we'll take the double integral of f over this region, and that'll go in the numerator, and we'll divide in order to get the average value of the function. So first I will compute the area of this. 500 minus 450 is going to give me a 50. And then 600 minus 575 is 25. So we'll just multiply those two guys together. The area of the region, which could be computed by a double integral, but that's not necessary in this case because it's just a rectangle, is 50 times 25, which is 1,250 square units, whatever that is. Well, in terms of area, it would be square units, but I guess it's number of units of, or a unit of labor times a unit of capital in this application. Okay, so that's going to go in our denominator. And then in the numerator, we'll have our function f, and we'll integrate from 450 to 500 for x. And then we'll let y vary from 575 to 600. And you can integrate with respect to y first and then x. That would be fine as well. Either way is fine because these are constant bounds. It's not going to change the computation or the calculation very much at all. So let's do that. And this is pretty simple. Just power rule stuff. Our production function is 100 times x raised to the 0.6 times 0.4. And I decided to integrate with respect to x first and then y. So we'll start on the inside. We'll work our way out. Leave the outer bounds alone. Bring that 100 down because it's constant. And y is being treated as constant when we anti-differentiate with respect to x. So we'll write that down. And then with our x's, we'll add 1 to the exponent and then divide by the new exponent. And then we'll evaluate from x equals 450 to x equals 500. Very easy. Just anti-differentiate with respect to x. And then substitute in the bounds and subtract. This 100 divided by 1.6 turns out to be 62.5. Y to the 0.4 is still there. And then we will have x to the 1.6. When we substitute in x equals 500, we'll have 500 to the 1.6 minus 450 to the 1.6. And I get these kind of ugly decimals. So I think I'll just leave that alone for right now. And that doesn't need to be in parentheses. Sorry about that. So I have 62.5 times 500 to the 1.6 minus 450 to the 1.6. And then we'll take our y to the 0.4 and anti-differentiate with respect to y. This is a constant and this is a constant, so I'll just write it down. Here I will add 1 to the exponent and then divide by the new exponent and evaluate from y equals 575 to y equals 600. And this is what we get. That doesn't simplify nicely, so we just get that there. And then I'm evaluating this at 600 and 575, and I'm subtracting. I'm just thinking of this as a constant, so I'm just bringing that out to the side and evaluating this at this point and this point and subtracting. That would be our exact answer. It came from taking the antiderivative with respect to x, substituting in the upper limit and lower limit for x and subtracting and factoring out the constants. And then we took an antiderivative with respect to y. And then we evaluated the upper limit and the lower limit. And then I would just use a calculator to get that not the exact answer, but a decimal approximation of that answer. So I'm still just entering that there. Close parentheses. When I get that. So it looks like I've got 64,635,827.9. That is our production level, or not our production level, but that is sort of the volume under this function. So we're taking a production level and then we're multiplying by some number of units of labor and multiplying by some number of units of capital. Now, if we take that and we divide by this area of the region R, which has got some strange units, number of units of labor times number of units of capital. When we take that and we divide by that 1250, that will give us the average value of that production level. So I'm taking my answer from the last step and I divide by 1250. And I get that. So this is approximately 51,708.66. And I believe in the problem statement, we were asked to round to the hundredths place. So that would be our answer.